So you're a data scientist that understands the importance of explainability to your AI solution. How do you go about incorporating explainability into the machine learning development cycle? What are the pros and cons of some of the most popular explainability techniques? And how do you choose the right explanation? What is a good explanation, and how do you even know if an explanation is useful? Hello, everyone, and thanks for joining us. My name is El-Sharif, and I'm a steering committee member at Aggregate Intellect. Today, we are very pleased to be hosting Violeta Misheva. Violeta is a data scientist at ABN AMRO Bank, one of the biggest Dutch banks, and she works on projects from various domains with different departments within the bank. She also spends part of her time doing applied research on topics such as explainability and fairness, and together with other colleagues is setting up a framework to ensure the machine learning models are developed in a responsible way. She started her data science career in consulting, which was her first industry job after academia. Violeta completed a Ph.D. in microeconometrics at Erasmus University in Rotterdam. During her academic research, she became fascinated with data algorithms, and that passion grew over time. Violeta likes sharing her knowledge with others, and therefore she facilitated data science workshops for online university that are and designed on platforms such as DataCamp and Udemy. And we are very lucky to have her today. Violeta will be presenting Explainable AI, a data scientist's user journey. To the audience, please post your questions in the chat, and we will be asking your questions immediately after the presentation. So without further ado, I will now turn the presentation over to Violeta. Please take it away.
Thank you so much for having me and for the nice introduction. I'm a big fan of the series, so I'm super excited to be here as a presenter. And now I will go to my slides. Yeah. Okay, so what's on the agenda? I will start with the bad news. What are the current urgent challenges of explainability, or also known as XAI? I will talk about how explainability fits in the machine learning development cycle. Before I briefly talk about some pros and cons of current popular explainability approaches, and then I will finish with a hypothetical data scientist user journey. Basically, how to select an explanation in a conversation with a stakeholder. And let's get right to it. What are some of the urgent challenges of explainability? And this is not by any means an exhaustive list. But maybe one of the biggest challenges is that currently it's really difficult to quantitatively assess and compare different methods. That's something that you might also recognize from your own experience, and something that we will come back to later in the talk as well. Also, in big organizations, it's really difficult to align all the numerous stakeholders that might require some sort of explainability. It's really difficult to understand what is the most suitable approach to them, and also to come up with the best way to deliver that explanation to them. Another big challenge is the lack of understanding on validity and monitoring of the explanations. You might know from personal experience that in general, monitoring machine learning applications in production is quite difficult on its own. But whereas we can validate the prediction of a model, we can just compare what really happened versus what the model said. There isn't really a straightforward way to compare the validity of the explanations. Furthermore, users lack control of the explanations. Very often, they're just given certain explanations, but they cannot do anything about them if they don't really agree with some of the explanations. Related to that is that it's really difficult to collect and provide feedback to the explanations, especially if we have a large stakeholder map involved, and we present to them the explanations through various channels or through various means. And last but not least, that's something that I noticed data science colleagues sometimes don't really acknowledge, is that post hoc explanations could very often be misleading. And that's not often reflected in the way that they provide these explanations to the stakeholders. but we'll talk a lot about that a bit later. Let's start with the first challenge. What is basically a good explanation? There's not much research out there, at least not one that really allows for a quantitative measure of goodness of an explanation. Although I found a couple of papers that discuss what is at least a good explanation for us humans. And this is not an exhaustive list of criteria. But a good explanation is one that is contrastive. So basically, we as humans want to understand why a prediction was made instead of another prediction. So if I, for example, am rejected for a loan, I would like to know what factors I should change to make my next application successful. A good explanation is also a selective one. Basically, we as humans can comprehend only how a list of a few important drivers contribute to an outcome. Even if we have a transparent by design model, such as a linear regression or logistic regression, but we have hundreds or thousands of features there, and even if we have a lot of domain knowledge about the topic, well, then it's going to be really difficult for us to comprehend how each of these features contributes to the outcome and how they might be interacting with each other. A good explanation is also one that is consistent with prior beliefs, or it's in accordance with our intuition. In other words, a good explanation is one that is believable for the receiver of the explanation. Of course, it's also quite difficult to properly define what believable means, and it's likely to be different for different users of the explanation. Moreover, a good explanation is a social one. Basically, it's part of the conversation between the explainer and the receiver of the explanation. What this means is that various users of the model or the system will need various levels of detail in the explanations. At the same time, a good explanation focuses on the abnormal. And we as humans tend to focus on abnormal causes to explain events. What that means in practice is that if we have some abnormal features that really matter for a prediction, we should include them in the explanation, even if they are rare. But at the same time, an explanation is one that is general and probable. Basically, it can explain many events. That kind of contradicts the previous criteria, but the way that I personally interpret it is that in the absence of an abnormal event, a general event is considered a good explanation. So, of course, it's really difficult to translate this list of factors into concrete measures for the goodness of an explanation. But I think that they're a good start of creating a checklist or creating criteria that these potentially quantitative measures should encompass. Another research that I found that deals with basically discussing whether explanation is good or useful is this paper, is the Metrics for Explainable AI paper by Hoffman and others. And the goal of their research is that a user is presented with an AI system and an explanation that basically details to the user how the AI system works. Basically, they measure the user's understanding, if it works, whether it works well, and whether the user is basically satisfied with the explanation, whether they properly understand how the system works. And there is no prior knowledge required from the user about AI, about the system in place whatsoever. They also propose a number of checklists and measurements for the goodness of the explanations, are users satisfied with explanations, how well the users understand the AI system, how curiosity motivates the search for explanations, and to what extent users' trust and reliance in the system is accomplished at the end of this whole exercise. So the difficulty with this is that although the checklists are very valuable, In practice, it's really difficult to expect users to go through very detailed and lengthy sort of surveys or checklists to provide feedback on the explanations that we have. So perhaps a shortened version of all of these measures could be a good place to start. Now, how do we go about incorporating explainability into developing a machine learning solution? Let's assume that we have a clear business problem. And let's assume that our input data is given. I know that in many contexts, that's too big of an assumption, but just bear with me. Then the first important task before we even go to the machine learning training part is to gather the requirements in terms of explainability of all various stakeholders involved. And remember, this was also one of the second challenges that we have. And why is it a challenge? Well, simply, there's not a straightforward and easy way to do this. And conditional on the use case that you're working on, you might have a very extensive list of stakeholders as well. Let's, for example, imagine that we have a machine learning application which decides whether we should grant a client a loan or not. So who would be the potential stakeholders in this case? We have, of course, the client to whom we should explain if they are rejected, why they were rejected. We have a loan officer or relationship manager that is processing the application. We have the technical team building this application and deploying it later. We have the business team that requests this application to be developed and that accepts the main risk of the application. Sometimes we also have a product owner or project manager leading the business team. Also internally, let's say in a banking environment, you're going to have stakeholders such as legal department, compliance department, privacy office, model validation, audit department. And in a domain like finance, we also have to explain the models, how they work, the data they're using to external regulators. So for this one use case, we could have a very lengthy list of stakeholders. And it's not a simple process to really understand what they might need from an explanation in a use case like this. But let's say that we have done that, we have done our homework. It's clear for us what every stakeholder might need in terms of explainability. And we proceed to developing an algorithm. Usually, we would apply explainability approach post hoc. And let's say that the solution is deployed into production. We might have some monitoring requirements in place for the model, of course, but also for the explanations. And ideally, we would like to continuously collect feedback from the user's interaction with the explanations. And here we have another challenge. Well, actually, a couple of challenges. First, as I mentioned earlier, it's really difficult to validate the explanations. We can validate the model because we can compare what happened versus what the model said, but it's really difficult to validate the explanations. And to make it even more complex, it's really difficult to continuously sort of collect this feedback from the various users of the explanations. And also, if at the beginning of the process, when the end users start interacting with explanations, and the explanations contradict, for example, their own domain knowledge and expertise, then users might stop using these explanations because they won't trust them anymore. That's something that I have witnessed happening a couple of times. So it's really a big problem not to be neglected. But let's focus now on what does it mean to basically apply an explainability approach and what explainability approaches can you apply? So I created this explainability taxonomy or flowchart, which tells you, provided on what you want explained. Do you want a static explanation or an interactive? And if it's an interactive, it's still an open challenge. That's not really one clear method out there that works very well currently. Then if you want a static explanation, you could go for a method that explains the data or explains the model. And if it's a approach that explains the model, we could choose a local explanation or a global one. And this is not an exhaustive list. There are more methods out there, of course, but this is just to give you an idea of the possible options that you have, and to also, it's something that data scientists, for example, could take with them during their conversations with different stakeholders, and could use as a starting point of these conversations. And it's okay if not all of these methods are known to you. Don't worry, because we will discuss some of them shortly. Starting with local explanations. One example method of local explanation is LIME, and I think that it was one of the first one, although it came out only in 2016, I believe. But LIME is great because it provides, it just traces a local surrogate model that explains individual predictions. It works for classification and regression problems. It works for images, text, and tabular data. And it's very sort of human and user-friendly because it can provide short and selective explanations. So it's good for lay people who are short on time. However, by now, there are a few established downsides of the method. Well, namely, it can be, first of all, unstable, meaning that different explanations, you could obtain different explanations if you repeat the sampling process. Also, another big challenge is that the definition of a neighborhood around a point is not a solved problem. Maybe from your own experience, you have played around with the Python package, for example, and you have noticed that depending on how you set the kernel settings, this could result in very big changes of the explanations for the same instance. And because they provide these short and sparse explanations, they're not always appropriate in compliance scenarios. Because from my experience, compliance professionals, they want to see what is the contribution of each feature for each instance. And last year, a paper came out about fooling LIME and SHAP. Basically, this leads to another con, which is that the explanations of LIME could be manipulated to hide bias. An improvement over LIME is a method proposed by the same authors called anchors. And anchors, they're also very intuitive. And the idea there is that you find a decision rule that anchors the prediction sufficiently, which means that changes in values of other variables do not change the prediction for that instance. So it has many pros. It is highly efficient and can be parallelized. It's arguably even easier to interpret than LIME, even to lay people, because at the end you just get ideally a short decision rule for an instance. They're also subsettable and provide a notion of importance, which you can measure with the coverage. And finding of rules is based using reinforcement learning techniques and not local surrogate models. So it's less likely to underfit the model. But it only works with classification problems. It does not work with regression problems. Of course, you can always translate a regression problem to a classification one, but you might sacrifice certain leaks in the prediction, of course. Another downside is that many parameters need to be configured. And there's not really a rule of thumb and no clear way to do so. And furthermore, coverage can be undefined in some domains. For example, how do superpixels in one image compare to another? It's really not clear. Shapley values is another popular method of local explainability, and by now is almost the default across many organizations that I have seen. Shapley values calculate the marginal contribution of a feature on an instance level compared to the average prediction. And why people like it so much is that it is perhaps the only method with such solid mathematical foundation and the respective properties it inherits. It can also provide full explanation for each instance, so thus it's better accepted in compliance settings. At the same time, the SHAP package, I don't know if you had the chance to play around with it. Besides the local explainability, it also provides global interpretability capabilities, such as feature importance, summary plot, feature dependence plot. And the good thing here is that these plots all use the same unit, namely Shapley values. However, one of the biggest downside is perhaps the larger computational time. That is, if you have hundreds or thousands of features and thousands of instances in your data. Though tree-SHAP is a fast alternative to kernel-SHAP, for example. In my experience, I think that the largest data set in terms of feature size that I tried it on had something like 12,000 features and maybe 60,000 rows. It was a mixture between tabular data and text data. And it took a few hours, perhaps 8 hours. So I just left it running overnight. But in that case, it didn't really matter so much because I didn't need an instantaneous explanation. So in some cases, the larger computational time is not really so horrible. Of course, it's not appropriate for sparse explanations since we include all of the features. And another downside, which is something that is applicable to all of the permutation-based methods, is that it suffers from inclusion of unrealistic data points when features are dependent. And the same as line, the explanations can be manipulated to hide bias, though Shapley values suffer from that to a less extent. Moving on to visual explanations, which is, in my experience, one of the most beloved types of explanations for non-technical stakeholders. Two popular approaches are partial dependence plots and individual conditional expectation plots. So partial dependence plots, they show the marginal effect of a feature on the predicted outcome. Another way to think of it is that the partial dependence plots are also the average across the IC plots. The IC plots, on the other hand, they display one line per instance, showing again how the prediction changes when the instance changes. So the pros of these methods is that they are easy to implement and understand by non-technical stakeholders as well. PDP plots, for example, they can reveal linear, nonlinear, or monotonic relationship between a feature of interest and our predicted target. And IC plots, on the other hand, could reveal heterogeneity. However, assumption of independence is perhaps the biggest potential issue with these types of plots. And IC plots could display only one feature meaningfully. With PDP plots, we could have 2D types of plots where we display two features, but for IC plots, we can only display one feature. And if we have really large data sets, then IC plots can become a bit overcrowded and a bit more difficult to read. Another visual explanation method, which is less often applied, is accumulated local effects. They also describe how a feature of interest influences the prediction on average. But in comparison to PDP and IC plots, they are unbiased, meaning that they work well when the features are correlated or dependent. They can also be faster to compute than partial dependence plots, and by default, they are centered at 0, meaning that the value at each point of the plot is the difference to the mean prediction. However, they can be a bit shaky with high number of intervals because to compute and to draw an ALE plot, you need to specify a number of intervals. And there is no rule of thumb on how to select and how to set the number of intervals. If you set it too low, that gives inaccurate plots. And there's no IC plot alternative here. So basically, we can't really say much about the heterogeneity. And if they do work well when we have correlated features, but interpretation remains a little bit tricky. So if features are correlated, they should be investigated together, not each of them in isolation. And although they're faster than PDP plots, they could be more difficult to implement in terms of code, because for PDP plots, there are a couple of stable packages. There's even implementation of them in scikit-learn. And there are not that many packages that really let you do ALE plots, at least in Python. And let's move on to the last type of explainability approaches, example-based explanations. One really valuable technique is called influential instances. And it's also very intuitive to understand how they work. So an instance is influential if deleting it from the data substantially changes the parameters or predictions of the model. It's very useful in debugging of a model, and you might have heard of it under the name of deletion diagnostics. And it can also tell us something about the model robustness, because would you really trust a model with a single influential point, for example? I personally wouldn't. And we can also use it to compare different machine learning models with each other. But it is expensive to calculate, because every time you exclude an instance, you need to recalculate and retrain the model. And it only takes into account the effect of single instances, not combinations of instances. And there is not really a clear cutoff of influence measure. Basically, what is a substantial change to the predictions of the model? That's something, up to us. There's also no stable library to automatically implement it, at least to my knowledge. So you need to do it yourself, although it is not that difficult to code. Counterfactual explanations are another method that is really beloved by non-technical stakeholders because they're also very intuitive. A counterfactual explanation of a prediction describes the smallest change to the feature values that results in a change in the prediction. Some of the pros are that counterfactual explanations do not have to be actual instances of the data, but can be a new combination of feature values. And they're very human-friendly and intuitive to understand. So you provide to your end-user explanations such as if the income of person X was 25% higher and they have one credit card less, then we would give them a loan next time they apply. However, they suffer from the so-called Rashomon effect, basically the issue of multiple truths or many possibilities, which could result in a change of the prediction. And if all counterfactuals of an instance are plausible and good, how can you prioritize between them? For each instance, even if we have five very plausible explanations, then how do you choose between them? And there's not a single stable package that works with standard Python libraries. I know there is a Libby, for example, but which is better established, but that works only with TensorFlow or Keras-based models, not with the standard scikit-learn stack. And last but not least, prototypes and criticisms. What are prototypes and criticisms? A prototype is a data instance that is representative of the data, and a criticism is one which is not well represented by the set of prototypes. So they can be used independently of a machine learning model or together with a machine learning model, and they are always actual instances of the data. You are also free to choose the number of prototypes and criticisms yourself. So it's a little bit like in the k-means algorithm, where you need to specify the number of clusters. That can be a pro, but at the same time, it can be also a con, because there is not really, again, any guidance, best practice, or rule of thumb on how to choose the number of prototypes and criticisms. And also the distinction between prototypes and criticisms is based on a cutoff value. And if you specify too many prototypes, they will inevitably end up in regions where the criticisms are. Again, one downside, as with the previous two methods, is that there is not a single stable package to implement this, at least to my knowledge, at least in Python. If you're aware of something, then please share it with me. I'll be really curious to know. Okay, in the face of all of these challenges, in the face of all of the methods that we saw and their pros and their cons, then what can a data scientist do? Where do they even start from? So basically, how can a data scientist pick the right explanation? And let's follow a data scientist on this hypothetical user journey, where again, we stick to our hypothetical example of predicting whether we should grant a client a loan, or in other words, predicting the likelihood of default. And of course, we can always start with first option of maybe training inherently transparent model, or second option, we can go for a black box model and explain it with the post hoc method. And let's say in our case that the data scientist tried a transparent model, but it's really not working that well. And when she tried something more complex, it really performs so much better in terms of precision that the stakeholder insists on having the black box model and insists on having it explained. So what does the data scientist do? And by the way, many of the examples come from this paper, Principles and Practice of Explainable Machine Learning. And half of them are, I came up with them myself. But let's say that our data scientist starts with the good old Shapley values, by now one of the industry standards, and she provides certain explanations, certain plots to the end user, to the stakeholder. And the stakeholder says, great, this looks great, but what would happen if salaries of our customers started to decline? Well, unfortunately, we cannot really use Shapley values to answer that question. And let's see what methods we can use to address that question. But before that, a little caveat of what to do if you have many, many features in the model. Do we really want to overwhelm the end user with hundreds of Shapley values per each instance? Perhaps not. So we could perhaps start with using Lime instead, where we could specify only X number of features for each explanation. Or if we really want to stick to Shapley because of their mathematical properties, again, we could present for each instance only top X number of features per instance. But whatever you choose, just be aware that with many features, there is high likelihood of dependence. And all permutation-based methods are less reliable when features are dependent. And do not forget that correlation is not the same as statistical dependence. Features could have low linear correlation, but they could still be statistically dependent. Another scenario is that the stakeholder might want to have diverse explanations. So he might not want to have explanations that point towards the same characteristic of a client, for example. They don't want to know everything about, let's say, their income history and earning over time. So how do you ensure sort of diverse explanations? Well, you could, of course, start with proper feature selection and only include features which have meaningful contribution to your prediction. You could perform also perhaps feature agglomeration, which is similar to clustering, but on a feature level, where the idea is that you merge similar features together. And last but not least, you could try dimensionality reduction, such as PCA. But how do you retain explainability after that? Well, let's say that you select 5 components because they explain a certain threshold of the variance that you want. So what do you do after that? Well, select only features which are highly correlated with the component of interest. But let's go back to answering the stakeholders' question. What happens if the income increases or decreases? So basically, we want to explore what happens to the prediction with the feature of interest. And one way to do that is with partial dependence plots and IC plots. So these graphs can help you understand how the probabilities would change with income. And then the stakeholder might say, interesting, that's nice, but can I get more insight into what the decision for Mr. X would be? But before I answer that, another hypothetical scenario. Let's say that the stakeholder realizes, okay, the income and the earnings of a client would be very much related to their age, to their years of experience, to their educational level. Can I still trust the plots that you showed me? Well, a better way to validate that is to perhaps use a ALE plot, the accumulated local effects, which tend to work better when features are dependent on each other. So the stakeholder is happy now, but she still wants to know, remember, what would be the decision for Mr. X? Can I get more insight into that? Okay, so for example, there are many ways that we could interpret that question and answer that question. First of all, which clients are similar to Mr. X? It's one way to interpret it. So we could approach it by, for example, using prototypes and criticisms. And by finding prototypes, meaning hopefully we'll find other clients that are similar to Mr. X, and understanding their prediction could also help us understand the prediction for Mr. X. Another way to answer that question is basically having the counterfactual view. Let's say that we rejected or we approved Mr. X for a loan, then what would happen if we play around a little bit with certain features, certain factors? Suppose that we change his salary and they missed one loan payment, then the decision boundary changes from being approved to being rejected. So the stakeholder is happy with that explanation, but they might have other questions. Well, would knowing their income be enough to change the decision? Well, we can try to answer that by finding or extracting the rules for that customers. And the way that we do that is by, for example, using anchors, which, remember, are designed to produce rules for selected observations. And hopefully, the anchor that we find for Mr. X would contain the income. And we could also calculate parameters such as the precision of the model by having that anchor and the coverage of the anchor itself. Now, let's say that the stakeholder says, oh, I think that actually our data for Mr. X is really inaccurate. I'm not sure we can trust it. If you exclude him, what would happen with the model? Well, what we can perform here is influential instances, or also known as deletion diagnostics. So basically, we could exclude Mr. X from the data, retrain the model, and then see what happens with the decision boundary of the model. And of course, a stakeholder might also know which features matter for all clients. So more the global view. Of course, we can employ a method such as feature importances. And the only thing I would add here is that you could calculate feature importances not only with tree-based methods, but also with any other type of a method. And last but not least, let's say that the stakeholder is happy with all these explanations we provided to her, but she might not want to go and look at multiple separate graphs. Well, can some of these explanations be displayed together and maybe interactively? And one such package that allows you to do that is ShapAsh. So here I have plotted a few types of explanations that you can extract with ShapAsh, such as feature importance, where you see the global feature importance, but you can also specify the feature importance for a subset. You have the local view, so local explanation, which is calculated based on, is calculated using either Shapley or line. And you can also look at the feature contribution. Again, it's calculated with either Shapley or line. So you see that just focusing on a single stakeholder, picking explanations to provide the right answers can be quite a long process. We might need to have similar conversations with other stakeholders as well. And I'm afraid that there's not always a single and easy way out. So Shapley might be great. I myself really love it, but it may not be sufficient on its own. And I know this is a lot of information, but if I need to summarize in a few important takeaways, well, first of all, unfortunately, there are still quite a few open challenges in the field of explainability. And my advice to you is if you work in a, well, not only bigger organization, that applies equally well to smaller organizations as well, but the moment that you have to apply explainability is to start having these conversations with the different stakeholders, map the stakeholders that you have in your use case, and try to understand to what extent do they need explainability and what type of explainability. And do keep in mind that there are also some scenarios and use cases where explainability or interpretability might not be desirable, needed, or applicable. Also, try to integrate it as early as possible in the development process. It should not be an afterthought, because if it is, it most likely won't be done properly. You don't want to have trained a very fancy, precise, state-of-the-art complex model, only to realize that in that domain and use case, you're really limited to something transparent by design. And one can also provide different levels of explanation depending on the context, needs, and end user. And we could provide different explanations for each of this, the end users. One explanation for a client, different for a credit risk manager, third for a technical team, etc. And a combination of methods could very well be valid. It's not either or. Because when it comes to explainability, there is no one-size-fits-all approach. It's a process rather than a single product, rather than a single method. So this is what I wanted to share with you. Thank you so much for your attention. I think we still have time for questions. And you feel free also to connect with me on social media. So this is my LinkedIn. You can just find me by my name. And I also have a Udemy course on XAI, so you can use this QR code to claim 30 days free coupon. So thanks.
Thank you, Violeta. I appreciate it. And we've received quite a few questions online and quite a few questions in advance. So we're going to try to get to as many questions as we can through the time we have remaining. So I'll start with, maybe I group them as best I can. We'll start with some of the technical questions. Is Anchor more stable than Line? Maybe we'll start with
that. In general, yes, but it is still highly configurable. There are quite a few parameters that you can tweak. And depending on the way that you tweak them, you might get different anchors per instance. But in general, yes.
Okay, and this was a question you shared with us, limitations of Line and Shapley and other methods. Are people working on better versions and better explainer tools?
I hope so, because currently there isn't a one method that is necessarily superior to others. That's why we saw so many cons. Sometimes the cons really were larger than the pros for each of the methods. So I really hope so. I really think it's necessary that the explainability community designs, more and better tools in the near future.
Yeah, and I'll add to that. It's an active research area, and that's what makes it exciting. And a lot of the problems are unsolved. That's why we're working on it.
Yes. Right? Yeah. Exactly.
Now, I guess you've mentioned something about identifying feature dependence in your data set. That's not necessarily the same as, so correlation does not mean feature dependence. Mm-hmm. Can you help us identify any methods for identifying feature dependence? If correlation is valid, yep.
Yeah, just standard statistical tests for dependence. Depending on what kind of features you have, it might be a different test, but just standard statistical test. Of course, it's a bit difficult because with correlation, you always, well, you usually test for one-on-one correlation between the features, whereas you might have multicollinearity, and with dependence, you have a similar challenge.
Yep. Okay. Thank you. Now, this, and I'm just going to reword it a little bit, but more of people are looking for guidance. What method do I use for what type of decision or what explainer? So maybe a decision chart to help people navigate which explainer method to use in what context.
Are you asking if this exists?
Yes. Okay. And I think the answer is no. Right?
The answer is no, it does not. And I try to illustrate with this example, the hypothetical user journey, although we, of course, focused on a particular use case, this could very well extrapolate to different use cases as well. And I'm afraid that it does not exist, but it would be really great and help the community if someone really creates it. So go for it.
Yeah, absolutely. Absolutely. It's an open area, and it would be a wonderful contribution to the field. Now, more from I'll switch to the questions that are on stakeholder management. Can you maybe talk about the cycle of reporting for different stakeholders? Are people looking for monthly, quarterly, ad hoc explanations? Just give us your experience with people interacting with explanations. Yeah.
Yes. Well, it will be, of course, slightly different within each context, within each domain. But for example, certain stakeholders might want to have these explanations only one time. For example, the internal stakeholders, which try to ensure proper data and model governance, such as compliance, legal professionals, model validation. Usually, they might require only a couple of cycles of the explanations. The same with the regulators. They might want to know, for example, what data are you using, what model are you using, how the model works. However, usually, let's say, the end users, people who use the model, the decisions of the model in some sort of a task and take the decision of the model in making decisions about a client, for example, they require continuous explanations. Usually, you would like to supplement the prediction of the model for each client with explanations for that client of why the model predicted that. So it really varies depending on the context, depending on the use case, and depending on the stakeholder as well.
Okay, excellent. Now, another question is, a lot of these visual explanation tools have their own visualizations, which might be a little bit difficult to read or interpret. How common, or what are your thoughts on the practice of extracting the explanation and maybe generating that in a customized visualization?
It could be done if it really serves your context better. In my experience, it hasn't really been that necessary to create completely a new explanation. You, of course, would like to modify it for the context, and you need to think about how you're going to provide it to the end user to make it easy for them to read it and to interact with it. But usually, most of them suffice.
Okay, yeah, and I think the question was really more of take that content and put it in a Tableau dashboard or whatever. I mean, have at it, try it, but may not be necessary.
Of course you can do that depending on what kind of tool is used in your organization, be it Tableau, Power BI, etc. Yeah.
Okay. Now, I guess there more of a question about the risk of confirmation bias. Are we potentially concerned that people are using explanation to justify what they want to hear in the first place?
Yeah.
Yes. Okay. Yes. Okay. It's possible. Yes.
Yes, it is. It is. I think that's definitely possible, and it's also rather tricky to solve and to approach. And I'm not sure that providing, let's say, very detailed explanation for a prediction is the way to solve it.
Okay. Okay, so I'll go back to, maybe I'll just turn to some of the backlog of questions we've had from some audience submitted in advance. There are, can you maybe comment on the intersection of maybe fairness and explanation? What is your thought on terms of how explanation can contribute to fairness and where it cannot contribute to evaluating fairness?
Yeah, that's a good question, and many people consider them jointly. In my organization, we separate the two processes a little bit. I do believe that explainability and just broader transparency about the process, the data, the model itself could help in detecting potential biases. But I don't think that explanation per se is the best way to test whether the data or the model is biased. There are many fairness metrics and approaches to do that. And I also noticed that regulators, at least in the Netherlands, in the financial domain, also are starting to clearly differentiate between those. And they, for example, would bundle explainability with broader transparency together, but keep bias and discrimination separate from the transparency and explainability domain.
That's really valuable insight, because it's common for those two concepts to be mixed up with each other, and they're really different concepts.
Yes.
Okay, beautiful. Now, as a practitioner, what is your perspective on some of the wrapper packages like Interpret ML that essentially take multiple explainer methods and put them under one roof, versus accessing the explainer method library package directly like LAM or SHAP?
Yeah, I think it's a matter of personal preference. The advantage of wrapper methods such as Interpret ML or AIX 360 is that they provide multiple methods under the same roof. So let's say you need to install the package only once. And I think that they're especially valuable for people who are just starting. Let's say data scientists who have little to no experience with explainability. But I myself tend to stick to the separate libraries and packages themselves, because they give me better sense of control. And yeah, it's just a matter of personal preference. I tend to go for the latter.
Okay. Thank you for that insight. And more of an example question. Can you give us an example in which maybe explaining a model caused you as a data scientist to go back and make some changes and fix something?
Yes, that definitely happened. I can't reveal too many details, of course, but it was a regression problem. It was also, I was just starting to look up different explainability methods. And in this case, the business stakeholders were a bit skeptical. It was the first time that they were facing machine learning models. So by applying different types of explanations to, let's say, the cases where the model was doing very well and the cases where it was not doing so well, we could figure out that we have recoded a couple of features wrongly. So we could spot some mistakes in the code and then fix them. And then also the features did not behave so weirdly anymore.
Okay. Now, I guess more of a question from a stakeholder management. In your experience, who is the typical consumer of the immediate explanations you're generating from your packages like LAM and SHAP? What's the job title that mostly interacts with those explanations?
Yeah, so it will usually be some sort of an analyst. In the case of banking, for example, it will be very often a relationship manager, person that interacts also with the client. So either a business analyst or a relationship manager, but very often also main stakeholder is, let's say, a product owner or product manager that is heading this team of perhaps business analysts, because they're also the ones who need to kind of accept the risk of a model.
Got it. Now,
so they'll be the daily users, yes.
Okay, so those are the daily users, and maybe follow-up questions. And what's the level of interaction of executive leadership with explanations, or what aspects of the explainability are they typically looking at?
I think that, and that could, of course, vary in other organizations, but from my experience, yeah, executive leadership cares more about the process themselves. They might not care about the nitty-gritty details about, okay, what kind of a model it is, but they really want to ensure that we have proper governance and procedures that ensure that the models that we develop in-house are responsible and they are transparent, they can be explained when necessary, and they are not biased towards any subpopulation group.
Okay. And unfortunately, we're getting close to the end of the time that we have. I wish we could make this a 10-hour session with you, but I think 1 hour is going to have to do for today. Before we wrap up, are there any final thoughts that you would like to share with us?
Nothing in particular, just thank you so much for having me. It's been a pleasure. I'm really excited about the field, and yeah, people should just feel free to reach out to me. And yeah, I would like to turn this into sort of a knowledge exchange. If you disagree with any of the statements I made, please make sure to reach out to me. I'm very open to receiving feedback on that as well.
Okay, well, in terms of feedback, I'm looking at the comments, and they're all just very positive and really thanking you for this great presentation. So on behalf of myself and everybody else in the audience, I thank you for a great presentation, and thanks all who joined us online and those who submitted questions in advance. To see more free content like this, please visit our website at ai.science and log in to access the slides from this and other sessions. Also, make sure to subscribe to our YouTube channel, ML Papers Explained, to get notified about all the live sessions and other free content we publish. This concludes our event. Thank you for watching.